Let's start recording. And okay, let's go. Speaker view. So, okay. And what I'm going to do, and you should all do this as well, is you all have it on Canvas. Go ahead, please, and open up the notes for chapter 1. And I'll do the same thing here. It's under Files, Intro to Probability, 8/23/17. Don't mind that. That's just the wrong date. But everyone should open up. And we have the notes on empirical and theoretical probability. And Catherine, you said what type of calculator? You don't need to have anything. I'm going to try to figure out a way to find a free online. But if you're going to get a calculator, I do recommend the TI. Oh, that's kind of cool. It's like the TI 84 Plus calculator. It really is a good calculator, and it will serve you well beyond just this class, but for any math class that you ever take in the rest of your life. So, are we ready to begin math? That is not the enthusiastic response that I was hoping for. I was hoping for a lot of, that type of thing, really a lot of excitement and enthusiasm, and I get nothing. So, okay. All right. So the first lesson is on empirical and theoretical probability. Of course, before we should talk about the difference between empirical and theoretical probability, we should first ask what exactly is probability in the first place before we divide that into two types, empirical versus theoretical. So in this class and in life in general, not at a very rigorous level, but for what you're going to need to worry about, probability is synonymous with likelihood. When I ask what is the probability of a certain event, I am asking what is the likelihood of that event. So for example, if you flip a fair coin, so how many outcomes are there when you flip a fair coin? Well, there's the two obvious ones, heads or tails. And then there's the two non-obvious ones, which is landing on its edge and hovering forever in midair without ever landing. We're going to assume that those two would just never occur and try to keep this really more realistic. So there's really two outcomes, right? Heads or tails. And if I said, what is the probability? What is the likelihood of it landing heads? I don't think we really need a deep understanding of mathematics for this. What would the likelihood of landing heads be in this case if it's a fair coin? Anyone? Just jump in. You can just say it.
50%.
50%. 1/2, 0.5, they're all equal to each other. Nice feedback there. So 1/2, correct? But here's a slightly deeper question. Let's say you work for, you work for the NFL, National Football League, and Super Bowl is coming up, and you are in charge of the entire Super Bowl phenomenon, and you realize that at the beginning of the Super Bowl in football, there was a very important procedure that must be done first before anything else begins. What is the very first thing done at the Super Bowl every year? What's the first activity done?
Coin toss.
The coin toss. Now, they don't flip a quarter. They get a disc that is constructed by some company. And so they go to the company and they say, hey, we need a fair coin because we are going to have this on TV and we want to do the coin toss. And the company says, okay, no problem. We'll manufacture that coin for you. They come along and they say, here it is. This is a perfectly balanced coin. And you say, well, how do you really know that it's perfectly balanced? And they say, well, you can trust us. And you say, well, you know what? We don't trust anyone. We want to do our independent investigation. So how do you determine whether or not a coin is fair? What is something?
Take an average or something?
An average of
several
what?
times.
Ah, so there's the word.
Flip it several times or whatever.
Flip it several times. Let's say you flip it 3 times and it comes up heads each of those 3 times. Would you conclude that the coin is not fair?
It's not weighted properly.
Well, that's the question. On 3 flips of 3, you flip the coin 3 times, you get 3 heads. Will you conclude the coin is not fair? So have you ever flipped coins before? In your life, you've never flipped a coin?
Yeah.
Okay. If you flip 3 coins, do you think it's possible that you'd get 3 heads?
Slight chance.
Okay.
Maybe.
Yeah. I'm not saying it's the most likely outcome, but it can certainly happen and you wouldn't be surprised, right? You wouldn't say, oh my God, 3 heads, that's crazy. No, you'd say, oh, okay, well, I didn't see that one.
I'm lucky. I'm going to Vegas.
Okay, there you go. You're lucky. But it's certainly a outcome that, while not likely, is not shocking. But if you flipped it 1,000 times and you got 1,000 heads, what would you say now?
Would you like an unfair coin?
It's most likely an unfair coin. So somewhere between 3 and 1,000, we flip from fair, or at least maybe fair, to, yeah, this one's not fair, correct? And we got to figure out mathematically, we're actually going to do the math, exactly what is that number where we transition from, yeah, maybe it's fair, to, yeah, this one's not fair. I mean, you can actually compute it and get an actual number, 13, 14, 20, whatever it is. You can actually do that, and we will actually do that in the class. But the point I'm trying to make here is that sometimes when you talk about probability, you can't always do it from a theoretical perspective, like, oh, flip a coin 1 out of 2. If I say, for example, what's the likelihood that it's going to rain tomorrow? Can you do an experiment like flipping a coin and getting an answer to a question like that? Is it going to rain tomorrow? But sometimes you turn on the Weather Channel and they say there's a 70% chance of rain. How do they do that? Where do they get that number from? So this is a difference between theoretical probability and empirical probability, the very first slide. Empirical probability is based on long-run experience. What that means is that, okay, I've gathered lots and lots of data. I've flipped lots and lots of coins. Or I've seen lots and lots of days where maybe it rained or didn't rain. And based upon all of this historical data that I'm looking at, I'm now going to predict what's going to happen in the future. I'm going to give you my likelihood of a certain event. So in the first slide, it says it's an example. Suppose today's forecast says there's an 80% chance of rain tomorrow in Northridge. What does that mean? It means that in the past, when the weather looked like it did today, 80% of the time it rained tomorrow. So we are going to use that historical data to give a guesstimate of what's going to happen tomorrow. That is empirical probability based upon experience versus theoretical probability, like flipping a coin 1 out of 2. We don't actually flip the coin. It's theoretical. It's theory. Theory says it should be 1 out of 2. Does that make sense so far? So suppose you roll a die. We're back to the first slide. Suppose you roll a die 100 times, and you get a 3 21 times. What is the empirical probability of getting a 3 in that situation? According to the data that you've taken from your 100 rolls, getting a 3 21 times, what would you conclude is the probability based upon your experience of rolling a 3?
21%.
21%, 21 out of 100, right? 21% of the time you got that result. So you know what? If you got to take a guess as to the answer, let's just use the use the data that you got. Now, what is the theoretical probability of rolling a 3? For theoretical, we ignore all of our data. We're not using it. What is the theoretical probability of rolling a 3?
3%?
How much?
3? Or
So
30? 30.
30%, would you say? Where'd you get that from?
3 out of 100. So it'll be 30.
Well, 1 second. You said 3 out of 100.
Yeah.
So again, the 100 was how many times you flipped it, correct?
Yes.
For theoretical probability, you don't flip anything. You're not flipping anything. It's just purely based upon theory. What should it be?
So
it should be 1/6, right?
1 out of 6.
So the answer is 1 out of 6.
Yeah.
Right? There's 6 outcomes. One of them gives me what I want, 1 out of 6, which translates mathematically to what as a percent? And you can use your calculator for this. 1 out of, and you should know how, yeah, approximately 16% or 17%, approximately 17%. So if we got a 3 21 times out of 100 to give us 21%, is that so far away from 17% that we say that this is an unfair die? Or do we recognize it in real life? Sometimes it doesn't give you exactly perfect answers every time. Right? If I got 100 times a 3, now I might start thinking, okay, this thing is weighted. But with 21, like you ever play, a game that requires dice, right? Backgammon or Clue or Risk or Monopoly or one of these games, right? You're not going to get everything exactly 1/6 of the time, but it should be roughly close if the dice are fair. Agreed? With me so far?
Yes.
Okay, so let's go to page number 2. Example. The graph below shows the results of 25 flips of a bent nickel. Now, if I give you a nickel, a regular good old-fashioned nickel that, just came out of the mint, I'd probably think it's fair and 50-50. But with a bent nickel, to be honest, I have no idea. Is it fair or is it not fair? Is one side more likely than the other? I don't know. So what do? We flip it 25 times. Correct?
Yes.
We flip it 25 times. Now, if you look at that graph, the horizontal axis are your flips. There's 25 flips on the horizontal axis. Do you see that?
Yes.
Okay. The vertical axis is the proportion of heads. So it could be 0%, it could be 50%, it could be 100%. Of course, 100% as a number becomes what? What is 100% equal to?
1.
1, right? So the graph goes from 0 to 1, 0% to 100%, 0 to 1. So let's look at the first dots. The first dots on the top left of the graph, dot number 1, represents the first flip. After that flip, the proportion of heads is 1. Was the first flip a head or a tails?
Heads.
Head.
It was a heads, right? If I have 100% heads, then obviously it was heads. The second flip, after the second flip, I'm still at 100% heads. So was the second flip a heads or a tails?
Heads.
Heads. But after the third flip, I am now at 60-something% heads. So what can I conclude the third flip was?
Tails?
Tails. In general, as you move along the graph either goes up or it goes down. If the graph goes up, what can you conclude was that flip?
Heads.
Heads. And if the graph goes down, what can you conclude was that flip?
Tails.
So what was the last flip?
Tails.
The last flip?
Heads.
The last flip, it moves upwards, right?
Mm-hmm.
At the very end of the graph, the 25th flip,
Oh, that's
right?
Jeff. Yeah.
That's a head.
That's a head, because at that point, the graph moved upwards. Now, the next part says, show how the proportion of heads was computed after the fifth flip. After the fifth flip, the proportion of heads is 0.8. Correct? Fifth
Yes.
dot, 0.8.
Yes.
Where do they get that from? 0.8.
It's at the line 0.8.
No, but But what must have happened on your end where you're actually doing the flipping? What must have happened for you to conclude that at this point in my graph, I should plot it at 0.8 as opposed to somewhere else?
You
Because it
flip
went
the
up.
coin. Oh, sorry.
Oh, sorry, go ahead.
Go ahead. Go ahead.
That's okay. Let her go ahead.
I just was saying it went up, so it was heads.
So how many heads must I have at that point for this thing to be true?
3,
In total?
4.
4.
1, 2. Oh yeah, the one that before 2 went up.
Right? It must be 4, correct?
2,
Yeah.
You agree?
Yes.
4 to 5, that's 0.8. Makes sense, correct?
Yes.
All right, so here's a real question. Based just on these 25 flips, what is the empirical estimate of the probability that this nickel is going to land heads?
80%.
60%.
Plus percent?
Okay, hold on a second. Someone said 80%. Let's address that first. 80% was after 5 flips. But now we're looking at 25 flips, right? We're looking at all of these flips. We want to use all of the information that we have at our disposal, correct?
Yes.
So we don't want to stop at 5 because we have more information than just 5. In statistics, you want to use all the information you have at your disposal. If you stop after 5, you're ignoring 20 extra flips. So based on all 25 flips, what would be your estimate for the probability that this nickel is going to land heads?
About 62%.
60.
It looks like
Close
about
enough.
62, 63, maybe 64%.
Closest to 62.
Yeah, it's kind of hard to tell exactly because it goes 0.6 to 0.8, not 0.6 to 0.7. So if you said something between 62 and 65%, you'd probably get credit for a situation like that. You know, when it's hard to read, you get a little wiggle room. But basically what you're doing is just going to the very edge of the graph and just reading the answer. It's right there. You don't have to look at anything prior to that. Right? All the information you need is right there at the end. Does that make sense?
Yeah.
And that is the empirical probability. Right?
Sorry,
Sorry?
I had so you know how you said to go all the way to the end of the graph
Yeah.
and then just see it. If you wanted a more accurate number, would you just count all the dots that are like every time it goes upward?
Yeah, so if you said, you know, I really care whether it's 62, 63, 64, if I really want to know what it is, then yes, it's certainly more accurate to actually count how many of them, you know, let's just do it quickly. Let's just go ahead and everyone independently count how many heads there are.
16, I think.
Well, don't just give it an answer. We're all going to do it.
No,
What the
I
hell?
counted. I had counted 16 before.
Counted 16 as well.
Yeah, it's 16.
Can you please repeat the answer again? Question?
So the question is, how many heads were there based upon what happened?
Like every time the line goes up, that's what you count, the dots.
Every time it goes up, it's a heads. That's correct.
It's 64%.
So there's 16 and therefore 64%. That will be the answer. And you know what? I amend my previous statement. In a case like this, if this was on a test or a quiz, then I would want you to count them because it takes you 30 seconds at most to do it. Probably even less than that. But if there were 1,000 dots, then I really wouldn't require that of you. Okay, but in this case, I would expect it, and you just got to use common sense whether it's appropriate to be precise or not. Okay.
I still don't understand how you guys got 16.
So look at the graph. The
Okay.
first one with the dot was a heads, correct?
Yes.
Second one was heads, correct?
Yes.
But then it went down. We're not counting that one.
Oh, you're only counting the heads, not the tails.
That's right. Just how many heads there were
okay.
of the 25 flips.
I understand how you got that. Okay.
Yeah, so every time it went up, it's a heads, and there you go. Okay.
Okay.
So you're welcome. So this leads to the next slide, to one of the most important principles in all of probability and statistics. It's called the law of large numbers. You might have seen that term before, the law of large numbers. It says, in random situations, now a random situation, just so you know, is something where you do not know what the outcome will be, but you do know what the outcome might be. So if someone's pregnant, let's say, and not getting into any of the more modern interpretations of gender, just from a historical 30 years ago perspective from my generation, how many outcomes are there for what the child is going to be? 2, right? Either a male or a female, correct? Do I know what it's going to be in advance? No, this is a random situation. I know what it might be. I do not know what it will be. Flipping a coin, I know what it might be. I don't know what it will be. Rolling a die, I know what it might be. I don't know what it will be. These are all random situations. So, in random situations, as the number of trials increases, the proportion of successes approaches a specific value. And that value we call the probability. In the last example, if I had to make a guess for the probability of it being a heads, I would have said 64%. Because even though it fluctuated in the beginning, by the end of the graph, that's where it was. If I had done 1,000 flips, maybe I'd have a slightly different answer, but I expect it to be fairly close. So look at this graph of 30 flips of a coin. What do you notice overall about the left side of the graph versus the right side of the graph? What do you notice?
On the
Huge
left, there's
drop.
more tails.
Yeah, on the left side, it's certainly a lot more fluctuation, correct?
Yes.
Whereas on the right side of the graph, it starts to stabilize. Hey, we have a new person. Okay, the person's gone. So on the left side, hello, you want to learn math too? No? Okay. So the left side of the graph, a lot of fluctuation, but as it moves to the right, it kind of stabilizes. And this is the idea of the law of large numbers. In the long term, the long run, it should approach a specific value. And what do I mean by approach a specific value? I mean stabilize around that value. Don't fluctuate away from it. In the short term, anything can happen, right? If I roll 5 dice, can I get 5 6s? Sure. It's rare, but it happens, correct?
Yes.
So short, but if I roll 1,000 dice, I do not expect that, because in the long term, I expect it to be roughly near what the actual likelihood is. So for this example, forget about the picture for a second, just theoretical. What is the probability of getting a heads for a coin flip? Not for this graph, just in general. What's the
50%?
50%?
Yeah.
What is the empirical estimate based upon this data?
55 or 60. Well,
50%?
it's 50. It's close to.
It seems close. It seems close to 50%, about halfway between 0.4 and 0.6, right? It definitely seems. I would conclude from this what? What will be my conclusion based upon this graph? All right, I just flipped a coin 30 times. What do I conclude?
In terms of how stable the coin is, or
No, the coin's just a coin, right? This is now in context. I flipped a coin 30 times. I plotted the proportion of heads as I moved along. What is my conclusion based upon my analysis?
The probability is you'll get 50% heads.
Well, but again, I'm looking for a conclusion versus a mathematical statement. Just what do you practically conclude?
That the longer that you keep flipping the coin, the more stabilized your.
That's mathematical. That's mathematical. Give me just conclude something.
it's pretty even. You're either going to get heads or coins, or heads or tails.
So state that in a non-mathematical way. Non-mathematical. For me, this coin's fair. Right? The coin's probably fair. That's my conclusion. Right? Why did I do this experiment? What was the point? I'm testing to see if the coin is fair. What do I conclude? The data suggests the coin is fair.
There.
Right? That's my conclusion. Right? I'm not talking about the details of long-term run and probabilities. I'm asking a question based upon the intent of the experiment. The intent of the experiment was to test whether or not this coin was fair. What do I conclude? Based upon my data, this coin is fair.
I have a question.
Yes.
If the table was vice versa, like the uneven side was on the right, will that mean the coin was not fair? Because
no, if it was fluctuating on the right side,
yes,
that would violate the law of large numbers. That would say that as I go further down the line, it does not stabilize somewhere.
Yeah.
And the law of large numbers says things stabilize the further you go. So if I reached a point where it was still fluctuating, I would go further because I've not yet stabilized around the specific number.
Okay, so it has to be stabilized.
Otherwise, there's no point.
Okay.
And it's not realistic, right? This is the law of large numbers. In realistic scenarios, things stabilize around what they should be.
Got it.
So if I told you to stop at, let's say, 15, and I said, what do you conclude? The answer would be, it hasn't stabilized yet. I can't conclude anything. Does that make sense?
Yes, it does.
Okay. So this is as far as I got in my class yesterday. I guess you guys are super duper faster than they are. And I don't want to have a skewed
Gap.
whatever the word is, between my 211 classes. So we're not going to go any further today. This is where we're going to end. If you just scroll down, just so you see to page, page 16, that is where the homework begins. So you at this point could probably answer, it looks like the first 3 or 4 questions.
So you're encouraging us to go ahead and just start the homework.
I would say, good. Yeah, I would say start immediately, but only do those questions that you know how to do at this point.
Okay.
So if you get to a question that's asking for, wait a second, we haven't learned that, then don't do it because you probably haven't learned it. Okay, does that make sense? Yes.
I have a question. So you recorded all of this, right?
Yes,
Is it going to be posted automatically so we can go through it?
It won't be posted automatically, but I'll post it.
Okay, it will be posted before 12 at night, right?
I will do my bestest.
Okay,
And you know what? And there will certainly be times that I just forget.
And just shoot you an email.
Just shoot me an email, okay? Every hour on the hour until I do it. No, you really have to start pestering me because otherwise I'll just, I'll do it later, I'll do it later. But if people are really bothering me, then it's like, oh my God, stop bothering me already, and I'll go and do it. Okay, so feel free to do that.
Okay, sir.
Okay. Oh, sir. Hello. Okay, that's great. So, are there any
sorry.
Okay. Are there any other questions?
No.
Yeah, what numbers did you say for the homework?
It looked like questions 3 to 4.
3 to 4? Okay.
3 to 4. Well, I mean, not just 3 and 4, but 1 to 3, 1 to 4. Let's take a look. I'll look a little more in depth. Hold on. Yeah, question 5, you're certainly not ready for. But I think that you can do the first 4 questions. Now, question 4 does send you to a simulator online, which I think should be active. If it's not, then you can skip it, but it should be active to answer question 4.
And that will be within the Canvas, or yeah.
It's on question 4. There's a you can just cut and paste.
Got it. Okay.
Okay, and if there's any questions, just again shoot me an email. Let me know.
Professor,
Yes.
do you want us to do those questions 1 to 4 before Thursday of next class?
That'll be wonderful. I'm not requiring listen, I'm not requiring the homework to be done at all. That's on you. But if you're gonna do it, I really recommend before next class.
Okay.
Because otherwise now you have twice as many questions for the next class. Right? Get them done right after you've learned it. It'll be the easiest for you.
Okay.
Okay.
Thank you.
Okay. You're welcome, everyone. I will see you guys on Thursday.
Thursday. Thank you.
Yes.
Bye.
My question.
Yes, I emailed you last night about adding the class. Do you think I'll still be able to add the class?
Veronica, yes, I have emailed my departments. Let's see if they've responded so far. They have not yet responded. I'm not sure. They told us not to add anyone, just to pass along all names to them, and then they will let me know.
Okay.
So as soon as I know, I will let you know.
Okay, thank you so much, Professor.
Welcome so little. Okay.
Sir, did you take roll?
Did I take a roll? Yes.
Oh, I don't think I was. I don't know. I was
You
having
came
trouble.
late. Is that what you're saying?
I was late too. I'll admit to that.
OMG. Okay, 1 second. Let me load up my
Same professor.
same professor. No, just me. I'm the only one. All right.
No.
All right, hold on. So let me go to my Canvas, which is
Oh, Professor, my last name is different from your roll call.
1 second. Just give me 1 second, please. To
Okay.
close out here. Attendance. So hold on. Miriam Demircian,
Yes.
is that you?
Yes.
What time did you come?
I believe it was 2:15.
Okay, so I'm marking you as late. Okay.
Okay, no problem.
Okay. Daisy Gonzalez,
Yes, I came at 2:05.
2:05. Had I already finished roll call?
I think you had just finished. I'm not sure.
Okay. Well, I don't think had I started the lesson for the day yet?
No.
Okay, so I will mark you as present. But in general, remember we begin at 2 o'clock.
Yes, Professor.
Oh, there's Sir again. Yesenia Perez,
Here,
what time did you arrive?
2:05 as well. Yeah,
Uh,
I didn't catch my name, so I assumed you were past it.
I see. And everyone else is here, so that takes care of everyone. Okay. All right. I will see everyone on Thursday, unless you have any remaining questions for me.
Sir, with me,
Huh?
because I'm in your Monday class, are you going to update that? Can you hear me?
I can hear you, but you're choppy.
You can hear me?
I know I can hear you, but is everyone getting the same static as me, or is that just me?
Yeah, it's
It's like staticky as you're talking.
Can you hear me now?
Now it's wonderful.
Okay. I wasn't here for yesterday for Monday's
Right.
class.
I will
Are you
go.
able to
I will go back and fix the attendance for that.
Okay, thank you. And also, I'll join your Wednesday class, but the next following Monday, I won't be able to.
You do the same thing.
Remember.
You do-
Okay,
do
thank
the
you
same
so
thing.
much.
You're welcome, so
Okay.
much. Okay.
Thank you. Bye.
Bye. Everyone else sticking around? What's going on? People want to talk to me or what?
Bye.
You can leave. Just go. Go.
Bye. Thank
Go.
you.
It's over. Just leave.
Have a good one.
Thank you. Thank you.
Yeah.
And then there were 3. And then there were 2. And then there was 1. Uh-oh.
Oh, Professor?
Yes.
Professor?
Yeah, I'm here.
Sorry.